Hello friends, welcome to my channel. Let's have a look at problem 121. Best time to buy and sell stock. So in this video, we're going to share two solutions. So our main purpose of this video is to first establish connection of this problem with the maximum subarray sum problem. So the second is to make an extension. So first, let's look at the statement. So we are given an array prices where prices I is the price of a given stock on the ith day. So we want to maximize our profit by choosing a single day to buy one stock and choosing a different day in the future to sell the stock. So we are required to return the maximum profit we can achieve from this transaction. So if we cannot achieve any profit, we're going to return 0. So this actually leads to the following observation. So the output of this problem is non-negative. So here are two examples. So in example 1, so if we buy at price 1 and sell at price 6, so we're going to get a profit 5. So in the second example, because the array is in decreasing order, so there's no profit, so we return 0. So first, let's also look at the constraints. So the constraints on the prices is the length. The length is bounded above by 10 to the power 5. And the prices are non-negative and bounded above by 10 to the power 4. So with that said, we are ready to analyze the problem and share the methods. So the first method actually is more direct or specific to this problem itself. So it's a linear traversal. So the idea is the following. So at each index or day I, so we compute the maximum profit if we sell a stock on that day I. So actually to carry out this approach, so we just need to use a running variable to record the lowest stock price before day I. Then we consider the difference. So we get the possible maximum profit for each of the day I. Then we just return the maximum. So that's method 1. So here actually we emphasize method 2. So the method 2 is actually a little bit indirect to this problem, but knowing the connection with the maximum subarray sum problem is what we want to convey. So let's use example 1 to fix the idea. So this is the example 1, right? So if we buy at price 1 and sell at price 6, so we get maximum profit. That is 6 minus 1, that is 5. So now if we examine the difference array, so what we get is, so 1 minus 7 is negative 6, 5 minus 1 is 4, and so on. So we get negative 2, 3, and negative 2. Negative 2 is 4 minus 6. So the above profit actually corresponds to the sum of 4, negative 2, and 3. So this array is the maximal sum subarray. So the reason is actually this. So we compute 6 minus 1, right? 6 minus 1 actually is nothing but 5 minus 1 plus 3 minus 5 plus 6 minus 3. So due to cancellation in between, so we arrive at 6 minus 1. But this is nothing but the difference, right? So that corresponds to 4, negative 2, and 3. So this example, or this specific small case, help us to digest the connection of this problem with the maximum subarray sum problem. So we could consider solving this problem by finding the maximum contiguous subarray sum. So the standard way for doing this is nothing but DP, or that algorithm bear a name that is so-called Kadane's algorithm. So here these actually are for method 2. So before we write the code, let me make some extension. So the extension is the following. So can you try to write solutions to find the maximum profit if we allow to do at most 2 transactions? So we also assume that the 2 transactions, so for example, we're selling at I1 and sell at buy at I1 and cell at I2 or G1, G2 respectively. So we want these two as an interval, they do not overlap, right? So this is actually an interesting problem to practice. So with that said, let's look at the solution corresponding to the two methods. So this is method 1, so linear traversal. So this is specific to the problem at hand. So for this, we want to first get the length of, so it's not necessary to get the length. Let's see, we can initialize a result which is whose final state is what we want to return, and then we can use a previous mean. So previous mean. So we can, because we want to find the minimal previous price and sell at a certain day. So we want this previous mean as small as possible. So as such, we want to set at the very beginning a large number. So we can set to be 10 to the power 5 plus 2, right? Because the let's see, the price is bounded above by 10 to the power 4. You can set 4 plus 1 or 2. So if you like, you can set it to float in infinity. This is very safe. Let's see. Next, we are going to traverse the prices. So for price or y in prices, so let's use y rather than price in order to avoid confusion. So for y in prices, this is the current day price. So then the profit, if we have, the profit will be y minus previous mean, right? So after this, we're going to reset the state of the result variable, that is maximum of result and the current profit. So notice that this profit can be negative, but we take maximum here. So overall, because of the initial state for result is 0, so this result will always be non-negative. And after this, we also need to reset the previous mean when we look at the next round. So this will be the update for this variable, previous mean. It will be the minimum of previous mean and the current price, y. So with that said, we are ready to return the result. So that's a solution corresponding to method 1. So let's look at the test. Yeah, it passes example 1. Now let's look at a generic check. Yeah, it passes the generic case. So with that said, now let's look at the second solution. So I'm going to copy this function signature here, and then we will mark this one as V1. So here we are going to write a solution based on difference array and DP, or the Kadane algorithm. So for this, I'm going to first mark that. So let's do this. First, let's make some preparation maybe. So I'm going to track the length, right? Length n of prices. So if n is less than 2, right? So we're going to return 0. Right, so there's no profit for sure. So next, we're going to consider the generic case. For this, we're going to introduce the difference variable. So that is prices I minus prices I minus 1 for I in range 1 to n. So as we get this difference array, so we can write a hyperfunction to do the Kadane algorithm, or DP, to find the maximal subarray sum, which corresponds to a transaction profit. So for this, let me write a hyperfunction to make the solution modularized. So the hyperfunction is nothing but Kadane's algorithm. So let's use this Kadane. So we're going to accept a variable, let's call it diff, And then what we are going to do is that, so let's write the length diff of m. So let's write it in a generic function. So here I'm going to use dp. So dpi will be the maximal sum of contiguous subarray ending at index I. Right. So first, let's initialize the dp table. So the dp will be 0 times m. So I want first to set the 0th index element, or the first element, just for convenience. So dp 0 will be the difference 0. And then I'm going to reset, update all the other dp components. So this is basically a for loop for I in range 1 to m, right? And then notice that dpi is the maximal sum of contiguous subarray ending at index I. So then we can consider two cases. First is if dp I minus 1 is less than 0, that is negative, right? So the maximum sum of contiguous subarray ending at index I would be the diff I itself. So that's one case. In the other case, if the previous sum is not negative, then we can extend the corresponding contiguous subarray by diff I. So in this case, dpi equals dp I minus 1 plus this diff I. So this way, actually, we finished reset all the elements in the dp table. So the return is nothing but the maximum of the dp. So notice that here the maximum of dp is corresponding to the maximum sum of contiguous subarray. So this maximum dp can be negative, right? If we have a diff array, so it has some negative components. But in the problem here, we require the output to be non-negative. So when we use this Kadane's algorithm, we just need to make sure the output will be always non-negative. So third one, so invoke and prepare return. So for this, actually what we want to do is that we just need to call the function. So we are going to return Kadane. So the diff, we have defined this difference an array. So but we want to make sure this is not negative. So this max will specify to this problem return. So with that said, I guess this also provides a solution for this simple problem. So now let's do a special case check. Oh yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes the generic case. So I guess with the second solution format finished, we achieved our goal. The goal is that we establish a connection of the current problem with the maximal sum problem of contiguous subarray. So actually you are encouraged to look at the contiguous subarray problem for locating its maximal sum. So with that said, I guess that's about it for this video. Thank you very much.